and the topic is ultra-high energy cosmic rays, which is a rather hot subject, I think, as we will hear from Roger. So, Roger, the floor is yours.
Thank you very much indeed, Mark, and thank you everybody else. Let me see, perhaps I should try and share my screen now. That'll be this one. Share, and then if I go into presenter mode, sorry, wrong one, presenter mode. That's that one. Do you see the screen?
It works.
Perfect.
Yes, perfect.
Okay, well, thank you very much. So my fourth topic is this time is ultra high energy cosmic rays, and I'll try and give you some sort of flavor of perhaps the history, but also where the subject might be going right now in a sort of general, I think, commonly accepted way. Although obviously I'm going to have to be a bit selective in the time available. But I will also, as has been my custom in these lectures, go off on a tangent towards the end of this lecture, suggesting some possibilities, some of which I think are new, for explaining what is being measured and observed. My collaborators over the years on this topic are listed at the bottom of the title slide, and the ones that are emboldened are the ones I'm currently working with right now on some of these topics. And of course, none of them should be blamed for errors on my part, but all of them should be thanked for what they have taught me. Okay, so let's I said I'd just show you some pictures. It's completely idiosyncratic, the list I've got here, but they're kind of interesting. In the top left-hand corner, there's Victor Hess, who in 1912 made balloon flights to show that cosmic rays came from outside the Earth, and in fact, from perhaps outside the solar system as well, eventually. And of course, he was a very brave man going up in this balloon to enormous altitudes at that time, wearing his hat. And he was quite confident that he would return to Earth, but it was a very perilous business, and that's experimental physics in the raw. Here's another experimental physicist, Pierre Roget, who understood about air showers and so on, and we'll come to his name again shortly. Next is John Lindsley, who was one. There were many reports of cosmic rays of prodigious energy in the literature, but real ones, I think, can be attributed to John Lindsley. And then a facility that we'll call Auger, which is one of several, actually, facilities that explore high-energy cosmic rays, but I'll highlight them slightly more, was led originally by Jim Cronin and Alan Watson, who did a tremendous job, as you'll see. And then three more theoretical people, although Fermi is not just not just a theorist by any stretch of the imagination, but Enrico Fermi, who contributed historically to thinking about cosmic rays, and here's the famous picture of him with his famous definition of the fine structure constant, if you look at the top left-hand corner there. And Chandrasekhar, who actually collaborated with Fermi, the one paper they wrote together that was relevant actually to this story, but he also, in his book, thought about acceleration of cosmic rays by cosmic ray, to which I will return. And then Ginzburg, who was a Russian astrophysicist and physicist who understood many important and correct things about cosmic rays, in particular where their sources were likely to be unsolved, and survived many big debates where he was basically came out on the winning side. So let's say just a little bit about cosmic rays on the whole, and I'm going to ultimately build up to trying to explain the higher energy particles, which are often detected on the Earth. They don't have to be, they can also be seen from space, but best to see them from at the moment it's mostly seen from the Earth as a result of giant air showers that are created, that create lots of particles. And of course you see a lot of muons which survive to the ground, and you can either see them in nitrogen fluorescence and so on as light flashes, or you can see them as particles, which are seen by a variety of ground-based detectors. Now, if you look at not the totality of the cosmic ray spectrum, but if you look above about a TeV or thereabouts, so here's a TeV here, a PeV, an extra electron volt, which is 10 to the 18 electron volts. So those who are unfamiliar with these units, I better get used to them. And then right up here, which is the extreme end of what's observed reliably, is a zeta electron volt, and probably nowadays the most credible high energy particle is about a third of a zeta electron volt. But if you think about them in their sources, then the source spectrum probably does go up to a zeta electron volt. And of course, if one thinks about the Large Hadron Collider and so on, or even the Tevatron, then one's down here in terms of the energies of the individual particles. If you care about how they're accelerated, which I'm going to do so in this talk, then this is what's relevant is, nature has accelerators that take you all the way up to the zevatrons, we like to call them zevatrons perhaps. If you care about them as interacting and having collisions, then it's the center of mass energy that's more relevant. And another way of saying what's going on here is 13 TeV center of mass at the Large Hadron Collider, and here's some futuristic circular collider up here, but this exists. And then what that means is that data from the Large Hadron Collider, treated empirically, is an extrapolated is not as big an extrapolation to try and it's an extrapolation, not an enormous one, to try and understand the detailed physics of the Shah models, which are used to infer the energies and directions and so on of the incident cosmic rays. So we see the spectrum here, and I'll return to this later, but we know a lot more about it than we did, say, 20 or 30 years ago, thanks to fine measurements. And notice that this is sort of scale. It's a flux of cosmic rays per unit energy, and so on. And then the spectrum steepens around about a PeV, and then flattens again just at a few EV. This feature is known as the knee, and that's known as the ankle. Again, we'll return to this a little bit. Just to give some scale. So as I say, if we take the actual energies, is the Large Hadron Collider, if you like, there. But it's always kind of nice to know, and this is a gentleman you might recognize, when he kicks a soccer ball rather well, he's up in the 160 joule, which is 1 zeta electron volt. It's 160 joules. And so in terms of energy, these cosmic rays are impressively energetic. In terms of momentum, it's a slow and sleepy snail. So that's the difference between, if you think about the momentum non-relativistically of relativistic particle, that's what it is. But so it's an impressive thing that nature is able to make these particles with these prodigious energies, 100 extra electron volts or thereabouts. 100 joules or thereabouts, sorry. Yeah. Okay, so here are just some of the detectors, and again, this is just a personal selection. There are many others out there, and I mean, this one doesn't have a caption, it's Cascade Grande. This is the lowest energy, this is ACE, it's looking at the very lowest energy, MeV, 100 MeV or so, cosmic rays in the solar system and beyond. Here's CREAM, which are flights from the Antarctic, and there's now actually a CREAM module on space station. Here's Cascade Grande in Karlsruhe. Here's AMS, which you've probably heard about, which is a magnetic spectrometer deployed on space station. And here's Auger, which I mentioned before. There's also telescope array and other facilities that are looking at the very highest energy cosmic rays. I like this picture. I've been there. It's a truly beautiful place in Argentina. And if you ever get a chance to go there, I seize it. And if we look at what they've sort of discovered, then ACE has made exquisite low energy spectra, as you can see here, MeV per nucleon up to about 100 or so. And you do fantastic isotopic decomposition of the cosmic rays, from which we've learned a lot. And it's got 4 consistent chronometers that give you the age of the particles. You go to CREAM, it and other facilities have been looking at the cosmic ray spectra as a function of composition up to the knee in the spectrum. If we go to AMS, that's been doing somewhat similar things. And I want to just draw attention to something that's been known about a long time, but is measured in a very exquisite way here. If we take the primary cosmic rays, these are the ones that we believe are accelerated, and then we just see them propagating to Earth. And this would include helium, say, carbon and oxygen, and so on. There's a spectrum, the number of particles per unit energy. We actually use rigidity, which is momentum per unit charge. But as you increase the energy or the rigidity, we see it's in these units, it's more or less constant. Whereas if we look at the secondary particles, which are made by collisions, spallation collisions of these primary particles hitting interstellar protons, so a proton breaks up say the carbon or the oxygen, and it gives you lithium, beryllium, boron, which there aren't a lot of intrinsically, but they are made as secondary particles from breaking up carbon and oxygen. We see the spectrum is steeper. And I'll come to the significance of that well-known observation as we go on. So I just wanted to draw attention to that. I think we go to Cascade Grande. This is looking at particles above that knee, between the knee and the ankle in the spectrum. And I'm not going to go into details here, but obviously there are fewer of these particles, and it's much harder to define a spectrum, but you're seeing features there in this spectrum, and the data, as I say, is getting better all the time. And then if we go up to Auger, and I think I'm going to return to this again, what we'll see here is, firstly, above the ankle in the spectrum, we see that we get more particles, and the extrapolation from lower energies would indicate. So it looks like there's a new source there. And I'll say a bit more about this, but also there is you were able to make a decomposition. It's a very hard business, this, but now I think it's generally agreed that medium and heavy nuclei are more and more a feature of the spectrum as you go to the highest energies. So there really is seeing medium and heavy nuclei as you go to higher energies. The protons are way down here. At lower energies, only up to about 10 extra electron volts. Okay, so those are just some of the detectors. Let me start by talking about the galactic cosmic rays, and I'm just in very round numbers. I'm going to talk about protons and then all the accompanying heavier nuclei, from GeV to say 100 TeV, rough energies. That's somewhat below the knee, but and I'm not going to be very precise about this, but if the primary thing that has been known for a long time, of course, is that when you observe them at Earth, then they're essentially isotropic to 1 part in 10,000 or maybe even better. And this indicates that they're not just propagating like at a particle accelerator, they're diffusing through the galaxy. And so here's a sort of cartoon of our galaxy. We're out here, and then there's cosmic ray sources, but probably mostly concentrated at these energies in the galactic plane, this part here, but they propagate through a much larger volume, and we kind of know that from chronometers and so on. And probably there's many more sources in the central regions of the galaxy, this red part here. So but what we see at Earth is very isotropic, which means that it's really a diffusive medium, these cosmic rays. Although they're traveling at the speed of light, they've got relatively short mean-free paths. And if we look at the actual observed spectrum, and if we measure it in terms of energy density of cosmic rays per unit log energy, then that'll go as about energy to the minus 0.6. These are all relativistic particles, so it doesn't matter energy or kinetic energy, it's all the same. But if we look, as you saw with that particular set of AMS data, that the secondaries to primaries have a spectral slope difference. In very round numbers, it's more complicated than this, but it's e to the minus 0.4 or thereabouts. And this tells you several things. One is that the particles themselves are probably getting one sort of acceleration rather than many contributions to the acceleration, because if there were many contributions to that acceleration, then the secondary particles would have more or less the same spectrum as the primary particles, and they don't. So it looks like what you get is the primary particles, the protons, the carbon, the nitrogen, oxygen, and so on, are accelerated in some accelerator, and then they make secondary particles as they propagate and diffuse through the interstellar and circumstellar medium. So the second thing that you can get from this is that the lifetime in the galaxy scales as probably about e to the minus 0.4. That follows directly from the secondary to primaries, and it basically means that the higher you go up in energy, the less time the particles stay in the galaxy. And this makes reasonably good sense, because their mean free paths ought to be longer and they ought to be diffusing out of the galaxy faster. But it also means you can correct the spectrum that you observe, this e to the minus 0.6, to get a source spectrum, so that the energy density in the cosmic rays, say, per unit log energy, will go as e to the minus 0.2, which means there's more energy at low energy, but not a lot much more. So there really is quite a lot of power that these sources are producing up at the 100 TeV or thereabouts range. Now, another thing you can infer from this is that we know from the ratio of the number of lithium, beryllium, boron secondaries to the primary carbon, nitrogen, and oxygen, we can just tell how many grams per square centimeter, the so-called grammage, that these cosmic rays have traversed, say at a few GeV. And it's roughly 5 grams per square centimeter at about a GeV. And this means that roughly half or so, slightly less than half of those, some of those elements are actually broken up into the lighter particles. But you can learn something rather more important from this, is that we know that the grammage through the disk of the galaxies, if we measure the number of grams per square centimeter of stuff through the disk of the galaxy, and astronomers know this sort of thing rather well, is about 2 milligrams per square centimeter. And so from the ratio of these two, we can relate the energy density of cosmic rays we see at Earth to essentially the power of the galaxy, the flux of cosmic rays leaving the galaxy. It's just essentially the ratio of those two that matters. And there's a considerable amount of uncertainty here, because we don't really know what's going on in the center of the galaxy, but an educated guess as to what's happening, it hasn't really changed over 50 years, is about 3 times 10 to the 33 watts, which is about 1,000th of the stellar luminosity of a galaxy like ours. Now, it isn't, as I say, there's uncertainty for the reasons I've given, but these are probably reasonable estimates, and certainly what I'll use going forward. So now, where do these cosmic rays come from? I'm not going to go through all the arguments here, but going back to Ginzburg and earlier, the culprit is now generally agreed to be mostly the remnants of supernova explosions. And basically, in the interstellar medium of our galaxy, massive stars, it's mostly massive stars that are doing this. Massive stars explode at the end of their lives, and they create these spherical shells of gas that blast out explosively into the interstellar medium. And those typically have an energy of about 10 to the 44 joules, and a somewhat probably, my guess is it's probably a bit high, but it's a commonly assumed assumption, a calculation of how many supernovae there are in our galaxy is there's about 1 every 30 years or so. This number has gone up as people have tried to convince themselves they're going to see another supernova with a neutrino detector. So obviously one hopes that happens. But if we just take that as round numbers as 1 per 30 years per galaxy, then it says the supernova power in the interstellar medium of our galaxy is about 10 to the 35 watts, which is about 30 times the cosmic ray power. So roughly, somewhere between 1 and 10% of the supernova power has to go into the cosmic rays on this interpretation. And if you don't like that source, then you have to find a more energetic one in the galaxy, and there are no real credible candidates, to be honest. And so really the only thing that it could be a supernova remnants. And in fact, there is prima facie evidence that these supernovae are accelerating cosmic rays. Here are observations at X-rays of a famous supernova remnant called Tycho's supernova remnant, and you can see relativistic electrons. These are non-thermal electrons outside the expanding thermal debris, and we see them defining a shock front going into the interstellar medium, and relativistic electrons being accelerated there. We can see this in a little bit more detail with more contrast here. We can see magnetic striations and so on. I'll come a bit back to that in a moment. And then we also have prima facie evidence that not just relativistic electrons are accelerated there, but also relativistic protons, from seeing evidence of pion features in denser regions with supernova remnants like this one here. So there really is prima facie evidence that these supernovae do accelerate cosmic rays, and I'll take that as a given going forward. So let's talk a little bit about this diffusion of cosmic rays. It's going to be quite important. The cosmic rays, as I said, are isotropic, but the sources are not, so that means they diffuse. But we know from spacecraft measurements in the interplanetary medium and what we infer about the interstellar and intergalactic media, that there's a spectrum of what are called Alfvén waves. So for those who don't know what an Alfvén wave is, let me just say that basically what you have is a plasma, which will be basically ionized hydrogen. It's permeated by a magnetic field. These magnetic field lines have tension in them, and just like tension in a string, they can sustain a wave, and that wave will propagate at the Alfvén speed given by the intensity and the density per unit length, and that speed is b over the square root of mu naught rho in SI units, and that will be something like about 1 to 10 kilometers a second in the interstellar medium. Now, what actually happens is that the interstellar medium appears, and all these media have lots of these waves around, and the waves with wavelengths comparable with the Larmor radii of the cosmic rays, which are about 10 to the 10 meters for a GeV cosmic ray, and obviously increasing in proportion to their energy. So when the wavelength is comparable to the Larmor radius of the cosmic ray, then you get scattering. There's a resonance scattering, and basically you get a diffusion in pitch angle, of the angle that the cosmic ray momentum makes with the magnetic field. And if the amplitude of the scattering wave is delta B, then in basically B over delta B squared wavelengths, then you get a turnaround of the cosmic ray. So that's essentially its mean free path. It's not a single scattering off a hard target. It's really a steady diffusion in pitch angle. And so this is responsible for the diffusion of the cosmic rays in the galaxy. And the waves themselves are produced probably in two main ways. And I'm not going to be able to have time to go into this in much detail here, but I mean, here we can see a sort of cosmic ray sort of diffusing through the galaxy, if you like, a cartoon model of the galaxy. So here's a cosmic ray sort of diffusing through it. But the ways that are doing the scattering, they're produced by the cosmic rays themselves. It turns out that if they try to stream on average faster than the Alfvén speed, say that's 10 kilometers a second or so, then they will excite the production of these Alfvén waves, which stop them streaming any faster. So that explains why their anisotropies are so low, is because if they try to escape the galaxy any faster, they create the waves which stop them moving any faster on average. And the other way of making these waves is to imagine that there's some great big spoon on the very large scale. And just like happens in fluid mechanics, if you stir up a fluid with a high Reynolds number, then you'll create a spectrum of waves of shorter and shorter wavelengths, and so there's a propagation of energy in wavelength or wave number space, if you like, the higher and higher wave numbers. And so you sustain a scattering turbulence by some external disturbance in the wave on very long wavelengths, and that makes a continuous spectrum of shorter wavelengths. And both of these will be important points that I'll return to. Now, it's clear that one thing is clear is if you think about just the motion of a charged particle in a electromagnetic field, it ought to depend on the rigidity. It's not the energy that matters, it's the momentum per unit charge, which is known to cosmic ray physicists as the rigidity. Again, I'll return a little bit to this point as well. Okay, so now let's talk about how the particles might be accelerated at shock fronts, and this is an old idea. In some sense, it has its roots in the ideas of Enrico Fermi. And if one makes imagines a shock front, let me take a shock front here as a cartoon of a shock front, and this is a discontinuity in a fluid, and in the frame of the shock front, we have from the upstream part of the shock, we have a fluid moving inwards with a non-relativistic speed, let's call it u, and it will leave in the downstream side of this shock front with a slower velocity, which is u over r, where r is the density compression ratio. So we have a fluid coming in with speed u and leaving on the other side with speed u over r. Now let's imagine there's a magnetic field here, and the cosmic rays are going to diffuse in this medium relative to the center of momentum frame, say, of this fluid here or the fluid there, and they're going to be scattered backwards and forwards, and so they're going to have a mean free path that is much smaller than the scale of the shock front. And this is indeed what we can actually observe is happening. And if we then describe the cosmic rays using a distribution function, the number per unit volume of momentum space, per unit volume of real space, and as a function of time too, then it is, if we just consider this in a sort of diffuse in the limit when the cosmic rays are diffusing through their background medium and gaining energy by being scattered off these diffusing features. And in particular, if we've got scatterers on this side, they're going to be approaching the scatterers on that side. And the particles that cross backwards and forwards across the shock front are going to gain energy because they're seeing approaching scattering centers kinematically. And that's essentially taken account of in this kinetic equation here. Here's a convective term, a diffusive term, and here's an acceleration term that is certainly important for when you're considering the scatterers approaching each other on either side of the shock front. And as I've written it here in the simplest test particle approximation, you can actually solve it. And it turns out, slightly surprisingly, that if we start off with a distribution function upstream that's coming into the shock front, then the downstream distribution function far down away from the shock front downstream is just going to be related by some Green's function to the upstream distribution function f minus, and it's just a power law. And the slope of this power law, again, this is the surprising part, is just 3r over r minus 1, where r is the compression ratio. And this is independent of the details of the diffusion. And for a strong shock in an ionized gas, which is the sort we have around a supernova remnant, r should be 4. This therefore evaluates to 4, and this is a momentum space distribution function. So in terms of energy, we multiply by p to the 4th, and so we get essentially a flat spectrum with almost as much energy and with as much energy logarithmically in the high energies as the low energies. And if we say, well, it isn't quite that compressive and there are other sort of weakening effects going on, then it's a little bit more than 4q. And this is just what we need to explain the source spectrum, as I advertised in an earlier slide. So this this simple sort of theory of diffusive shock acceleration, as we call it, is able to account for a lot of the features of that are inferred about the cosmic ray sources. And but the real world is of course much more complicated, and there are many sort of difficult problems. We've got to consider the details of how the diffusive the Alfvén waves that are doing the scattering are sustained. The pressure has to be included in the jump conditions for the shock front here, so the compression ratio will be affected in two competing ways. Actually, can be more or less this value R because of the cosmic rays themselves. And then a very important point, which I'll return to, is we have to ask ourselves the question about this F minus here, the particles that are coming into the cosmic rays, into the shock front, sorry, are they low energy particles, very low energy particles that are exalted by the shock front and given very high energies, or are they already existing cosmic rays that are further accelerated, re-accelerated, if you like, in the shock front? And both of those can happen. So those are some details. Let's just talk about this a little bit more, because this is going to be very important, and I really can't do justice to the issues here, but let me just give a cartoon of, say, one of these supernova shock fronts. Then I've sort of emphasized this scheme that the mean free path is going to increase with energy. So what that means is if you've got GeV cosmic rays near a shock front here, and this is upstream, then they're going to be able to not stream very far upstream because their mean free paths are short. TeV particles can get much further upstream, and then if you can get up to PeV particles, which is a stretch for the supernova shock fronts, then they go a long way upstream and will basically escape the shock front. So and if we look at some sort of intermediate energy here, we'll see a distribution function that looks like that, and not surprisingly, that is quite unstable. And so the cosmic rays, it isn't a contrivance. They really should be creating in these shock environments, they should be creating the scattering Alfvén waves, which prevent them from escaping and allow them to be accelerated to very high energies. There are mechanisms that are invoked to do this. I won't have time to go into these, but I will just sort of say that my own personal preference, and here I emphasize I'm in the minority amongst my colleagues here, but is that what is actually goes on is that the escaping cosmic rays far ahead of the shock front are unstable through an Alfvén wave instability known as the fire hose instability, and these create quite long wavelength Alfvén waves, and they make essentially a spectrum of shorter wavelength Alfvén waves that do all the scattering downstream. Other models have these particles making one of these instabilities here. That one is quite irrelevant, but these two are strong candidates for what's going on. And that may well, all of them are obviously happening, but it's a question of what's most important. And I would claim that, and I think most other people working in this field will claim that one of these two is most important. Another very important feature of thinking about this, and this is something that many of the simulations don't capture, is that real shock fronts are spherical. And that means that if the mean free path is more than UR over C, where U is the speed of the shock and R is the radius of the shock front, then those particles are not going to return. They're going to essentially escape. And so this really determines when the highest energy what the highest energies that can be accelerated are. And the final point that should be made is, particularly in the context of the supernova remnants, is that when you come to consider the implications of all of this, the particles that are transmitted downstream are going to find themselves in an expanding medium, and they are going to lose energy as a result of that expansion. So a gas that basically loses energy as a result of the expansion. And that has to be taken into account when you try and figure out how efficient all of this is. Now let's turn from these lower energy particles to the ultra high energy cosmic rays and think about some of the same considerations. The first thing that's important is that the losses that that matter here are not the sort of spallation losses that we saw in the interstellar medium, but instead are interactions with the microwave background. And at this range of energies from about 3 to maybe 100 extra electron volts, a proton, it's different for the other particles, but the protons are good to make the point. The protons will be subject to losses which sap energy from them and give them a limited range because they create pairs, electron-positron pairs on the microwave background. When we go to even higher energies, around about above an extra electron volt, then you start creating pions and the range gets even shorter. This is the sort of famous GZK cutoff. And there are many implications for this. That firstly, the sources are nearer than about 100, have to be nearer than about 100 megaparsecs at these very highest energies. And there's some qualification that has to be made if we don't look at protons. As we say, our very highest energies are not protons, but still it's true that the particles, the sources have to be pretty close to us as we go to the very highest energies. And then the second implication is because the range or equivalent of the lifetime of these particles is short, gets very short, less than 100 million years at the highest energies, then that means that although we may not see such a large energy density of the ultra high energy cosmic rays from our original spectrum, the fact that they don't live very long means that they do have a quite impressive luminosity density or power density. And it works out to be very roughly a few percent of the cosmic ray luminosity at, say, GeV energies per galaxy. So these aren't just some collector's item, these highest energy particles. They are actually a significant amount of power, and the source has to explain that. But and I emphasize again that composition is very important here, and I'll keep emphasizing this point. So we've learned, again, I'm not going to do justice to a huge amount of work that's gone in from the Auger and telescope array and other collaborations, but just to give you two, I think, key recent developments really over the last decade is firstly, anisotropy, after many false alarms, is now a real thing. It really is a significant above about 8 extra electron volts, and not at the very highest energies because you don't have the statistics to demonstrate anisotropy, but certainly above 8 extra electron volts. There seems to be anisotropy as shown in this map in galactic coordinates here. There's no obvious source for it's about a 10% or so effect. There's no obvious source of these particles, but that may not be such a surprise because there could be many sources for one, but not too many, but also the galaxy itself turns out to be a significant deflector. So we have the actual sources may be in a different direction from where the particles are arriving. The other important thing is, and I emphasized this before, but let me say it again, is that the composition, one's looking at medium and to some extent heavy nuclei. Here's a best guess decomposition from the Auger data above the ankle here. And again, one sees, in this case, A between 5 and 22, say, and the spirit of this is quite general. I think the different collaborations are differing in the details on these spectra, but I think everyone will agree that, I think everyone agrees now that the highest energy particles are probably not protons. Okay, so where are the highest energy particles coming from? Where does Eden Hazard get his football from? And well, returning to a theme of the jet talk, if we're going to say there's an electromagnetic accelerator there, if you want to make a high energy charged particle, you want to use electric fields or potential differences, then the most simple-minded way to get a voltage of, say, a zetavolt, just for the sake of arguments, then you've got to find a 10 to the 40 watt source, and there aren't very many of those around. And so for that reason, people have turned to active galactic nuclei and the jets. Here's 3C273 again, a nearby quasar, and here's the jet, and there's probably there's that power there, probably almost that within reasonable close to that power, and a voltage probably there near a spinning black hole at the center. So you've got the possibility of making a very high energy cosmic ray there, an ultra high energy cosmic ray. But the problem is that these quasars are mostly very distant. And the other problem is they're extremely bright objects. And so the problems you have with the microwave background are really serious there, because you get a lot of opportunity for photopair pion production and so on. So to evading that is very hard, and you have to accelerate a long way away from the black hole to make this credible. Same sort of thing applies to the gamma ray burst, which I mentioned in the jet talk. And those gamma ray bursts are, they have the same problems. They're even further away, probably, the credible ones, and they're even brighter. So it really is a challenge to get the particles out of those sources. Another possibility that people have suggested, which is again came up in the third lecture, if you like, are the magnetars. But if you imagine making one with a millisecond period, not with the 5 or so second periods that are observed today, then that could also be a prodigious accelerator. This is a possibility, I would say, still, but there are serious challenges associated with making the cosmic rays that way. And then another thing that over the years physicists in particular have written papers on are sort of exotic, sort of top-down mechanisms that invoke some usually cosmological entity which breaks up in some way to give you extremely high energy particles which cascade down to low energies. And so these cosmic rays are in fact just all losing energy. The argument against that is really rather a strong one, is that it's very hard to avoid making a much larger gamma ray background than the one we measure and fully account for by active galactic nuclei. So I think most people now accept that the cosmic rays are not a top-down model, but they're bottom-up in that lower energy particles are accelerated up to these almost zetterelectron volt energies. Now, the alternative to these that I'm going to discuss a little bit here, and I actually think might be right, is that it's actually intergalactic shock fronts associated with clusters of galaxies rather than any of these sources that are responsible for the highest energy particles. Again, this is probably a minority viewpoint. It's not an original viewpoint, but I should say, but it's probably a minority viewpoint. And the arguments against, in particular, the AGN are not that good, not that strong. But I think they're sufficiently compelling that one should take this alternative seriously. And it certainly doesn't have the problems of having high radiation densities. It's about the darkest place in the universe. So let's say a little bit about just sort of sketch the idea here that my colleagues and I have been thinking about. Again, is if one looks at a cluster of galaxies, and this is just one of them, the Perseus cluster. It's not the one we actually favor most, but it's one that is a good exemplar. These are all the galaxies in the center. There's about 1,000 galaxies in the center. They're all clustered together in a relatively small volume. So there's a large gravitating mass there, about 10 to the 14.5 solar masses worth. And there's a lot of hot gas in there. This is all this hot gas. It always looks to me like a Halloween mask with the eyes and the mouth and so on. But these are bubbles made by radio sources. I think I said this last time. And this is all the hot X-ray emitting gas there. And that was heated up from the intergalactic medium by passing through a strong shock front, which probably has a high Mach number, and is quite capable of accelerating cosmic rays, just in much the same way as a supernova shock front is. But instead of having the gas moving outwards, we have the gas falling inwards and passing through this schematically shown strong shock front. And we know quite a bit about that gas. We know that the entropy increases with radius, so it's passed through a shock front. We know there are heavy elements there, so it's gas that's been processed by galaxies. The typical radius is in astronomical units about a megaparsec or so. And we know that there has to be almost certainly strong scattering at that shock front that's made at the shock front by the particles themselves. And the general scheme is that the particles that can be accelerated in a shock front like this, if we just essentially scale from what we know happens at supernova remnants, the particles that can be accelerated have energies in the 10 to 100 extra electron volt range. Those are the maximum energies that you can get. Other rigidities are consistent again with the composition that's reported for these highest energy cosmic rays. Now, this is where the story gets a little bit more interesting, is that if you consider not just the particles that are transmitted downstream, which was what gave you the agreement with the cosmic ray spectrum of what is seen at Earth, but instead, if you consider the particles of the very highest energy, if they stream far enough ahead of the shock front, here shown out, say, get out to that point there, then they're not going to get back again, and they're going to basically escape. But those particles have a lot of pressure compared with the surrounding intergalactic medium. And the contention is that those particles are going to be fire hose unstable. They're going to have this instability caused by their pressure. And this creates a turbulence, say that's initiated, say, at this distance here, and then those alphane waves are then convected downstream towards the shock front. They create shorter and shorter wavelength waves, which are responsible for the scattering of lower and lower energy particles. But after the particles have escaped, their energy density and pressures are going to go down, inverse square law and all of that from this source, and they're not going to be able to create scattering waves at all. They're just going to propagate in the ambient intergalactic medium, which has very little scattering, and so they're going to propagate pretty close to, in an uninterrupted way, to come from, say, something like a cluster like the Perseus cluster, or more reasonably, actually, the Virgo cluster, which is the one that M87, the Event Horizon Telescope, source is in, and they're going to propagate from there to Earth. So, sorry, let's go that way, there we go. So essentially, they can spend more time being accelerated, these cosmic rays, than propagating, which is the opposite of what happens with the galactic cosmic rays. So what I've told you about so far is a story which I think is sort of generally accepted, that the galactic supernova remnants make the galactic cosmic rays up to, say, about 100 tera-electron volts, for example, and then a more speculative contention that it's the shocks around clusters of galaxies that make the highest ultra-high energy cosmic rays. So what actually makes the cosmic rays between the knee and the ankle? And so here's the ankle and there's the knee, here's zeta electron volts, extra electron volts, and so on. And and so, as I say, the supernova remnants, probably supplemented by hot stars, are responsible for this region here. And the contention is that the clusters, and possibly I think the jets from AGN could still be the primary source, are for these highest energy particles above the ankle. And then for this range that's being explored by Cascade Grande and other telescopes between the knee and the ankle, the prime candidate, I think, is probably shocks associated with galaxies themselves. A secondary candidate, as I say, one should take seriously, are probably the pulsars. So let's talk about the galactic shocks, and this would be part of our story. Basically, this is just a cartoon of, say, of our galaxy here, the spiral galaxy and so on. It's going to create an outflow, a shock, which is going to be fueled by supernova remnants in the disk of our galaxy. And here, looking at the disk of our galaxy, this is an image of the X-ray telescope Rosetta. We can see these features here. And that's sort of reminding us that it may not just be, the wind may not just derive from local supernova remnants, it may be dominated by an outflow from the center of our galaxy. They call this ultra-fast outflows. I think they were attracted to the acronym. And although it's not strong at the moment, in the past it could have been much stronger. And that drives a wind, like the sun drives a wind, outward away from the galaxy. And at some distance, perhaps 100 kiloparsecs or thereabouts, it's going to pass through a series of shock fronts. And those shock fronts can, can accelerate cosmic rays. And so it's almost like the inverse of what I've said is happening at the cluster shocks. Here we've got an outflow and a spherical shock front, bit more like the supernova remnants. And, and the shocks, particularly where you stop the wind, can be those that can accelerate cosmic rays in this knee part, in this shin, if you like, part of the spectrum between the knee and the ankle, in the peta-electron volt range. So the peta-electron volt particles are accelerated at these galactic shocks, and then some of those particles are going to get reflected back into the galaxy. They're going to escape upstream, get into the galaxy, and we'll observe them at Earth. So they can be the particles that we observe at Earth, but also some of them are going to go downstream and then escape from the galaxy altogether and get out into the intergalactic medium, where until they get to interact with the microwave background, they're essentially eternal. So they're going to live for the lifetime of the universe in the intergalactic medium. And so what we've actually been working towards is trying to establish a hierarchical model where we combine all of these features. If you like, we start off with very low energy particles, which might be accelerated at the supernova remnants, or there's other possible sources of them, including the hot stars. We've got the GeV to say roughly 100 TeV cosmic rays that are accelerated at the supernova remnants and then propagate around the galaxy and account for the observed spectrum. And some of them escape upstream. I think we now recognize more than we did in the past that the ones that escape upstream are pretty important. They're only the highest energy particles, but there's an evolution of the supernova remnant. And then there are some that are transmitted downstream, and they have to escape the galaxy before they get re-accelerated. And I think that's a constraint, but it's not a difficult one. The PeV range particles, if you like, the contention is that those are accelerated at these galactic shocks, say here, some region sort of around like that, and they're observed at Earth, transmitted in the intergalactic medium. And as we already know, and there's good reasons to explain this, that they're medium and heavy nuclei. And then the claim is that those not from our galaxy, but from galaxies closer, say, to the Virgo cluster or the Perseus cluster, are going to be, they've still got, energies of, say, 100 PeV or even an EeV. They then get carried into the shock front surrounding a cluster or some other large intergalactic mass concentration, and they're further accelerated. And those that escape upstream can propagate to Earth and be observed by the Auger telescope and so on. And so that's a sort of outline of a more general scheme. And I think that the important thing to say here is the test of this and other models like this, I think is going to be the composition. And as the composition and the spectra of the different elements gets better and better defined, that's going to be more and more constraining of a model like this. And models, alternative models, say those associated with jets and so on. So just to summarize, I hope I persuaded you that there's good evidence that galactic cosmic rays are accelerated by supernova shock fronts, but there are many puzzles too associated with making the details that are now being provided by these wonderful cosmic ray telescopes. The ultra-high energy cosmic rays, anybody who works on a particle accelerator on Earth ought to be impressed by this. And the sources are a significant amount of power in a cosmic sense. My colleagues and I would say probably the best candidate is intergalactic shock waves, but active galactic nuclei are a strong contender. And it's interesting to think about a hierarchical model where, in fact, it's holistic. They're all linked together. So the lowest energy particles then feed higher energy particles and so on. It's a sort of cosmic plutocracy, if you like, and trickle economics, if you like, and so the very few very highest energy particles actually began their life not in that shock front or not in that source, but in an interstellar medium like the one that surrounds our sun. And so this combination provides I think an opportunity for testing it using, as I say, improved composition, spectra, and isotropy measurements. And so it's an exciting time in cosmic ray physics, and I hope I've been able to convey some of that. Thank you very much indeed, and again, keep well.
So, thank you very much. This beautiful talk. We have time for questions, so please raise your hand if you have questions. I can see Peter Tiniakov. You have to unmute yourself, Peter. You are now. So go ahead.
Yes. Hi, Roger. Thanks for a very interesting talk. I have a couple of questions. The first one concerns your proposal of acceleration of ultra-high energy cosmic rays in the intergalactic shocks. In the intergalactic medium, I would normally expect there are mostly protons and helium. So where do you get these heavier guys there in sufficient amount? I would expect you would spend much more power accelerating protons in this same region than you would just by the number get heavier elements. What would be 10�3 factor or something like that, perhaps?
Right. This is where the sort of composition becomes very important. The contention is that the what you're really accelerating is you're actually re-accelerating the very highest energy particles that are made by local galactic shocks. So we've got these local galactic shocks, and we're seeing a version of those particles, the ones that escape upstream. We see them at Earth in the shin part of the spectrum, and those are heavier particles. And the contention is that you've got to work at a given rigidity, not at a given energy. The spectra I showed you are energy, and it really is rigidity that matters. And the contention is that if you do it integrating over the composition of what is likely to escape upstream from a galaxy like ours in the vicinity, say, of the Virgo cluster, then that will have preferentially these medium and heavy elements, and they will be the ones that will make it up to the highest energy, highest rigidity as they escape. And if you plot it in terms of rigidity, it doesn't look quite so alarming.
But did you ever estimate how many protons you would need to accelerate just because they are there?
Yes. Oh yeah. I mean, there will be protons. Of course, there will be there. But it's a given rigidity that it matters. Remember, we're talking about what's plotted usually is the energy of the particle, and then the momentum per unit charge, or iron or something like that. Momentum per unit charge is much less.
Do you then expect that Virgo is going to be the brightest thing?
It's more
big cluster and very cold.
My colleague Naomi Gerbers has actually done quite a lot of work on that. It's complicated. It should be a prominent source, but there are other accessible sources across the sky, and you can't have too many of them because you wouldn't see any isotropy. So it's a sort of balance. So I think oversimplifying a more complicated story, you do expect to see Virgo, but not the same place that the optical and radio astronomers see it, because the cosmic rays from Virgo will be significantly deflected by the large-scale magnetic field associated with our galaxy. Okay. So, but it isn't just an exclusive source. It's a prominent source in the distribution of large-scale structure.
Then the second question is about to the last part of your talk, of your hierarchical model. So if I understood right, you sort of have three at least different sources. But how do you adjust three different spectra so that they form a nearly perfect power law at the end?
Well, it's not okay. Wait a minute. I'm still on this. So
you sort of three
that's
different.
That's not a power law.
Well, it's not exactly power law, but it's quite close to power law. I mean, well, I would worry that you would have steps if you have three different sources and not adjust them very carefully.
Well, I'm not sure how well this is working, but I would say there are steps there. There's in fact, the cosmic ray spectrum, a true cosmic ray physicist say, no, there isn't a knee there. There are many knees. And they use the Latin coinage to express that thought. So they actually have more than one knee. And then there's the ankle here, which is a rather steep feature. And then if you look at the Cascadi Grande data, which I think I showed, you can see wiggles that they claim are significant there and so on. So it is more complicated. And I don't think it really is that smooth, but you know, if you're more impressed by the smoothness than the wiggles, then I would say diffusion is an awfully good way of smoothing things out.
It's a quantitative question. I mean,
yes, absolutely, absolutely. That's why we're working on this, because you know, I think the observations are now ahead of the interpretations, and I think you know, not necessarily using the particular ingredients that I've presented here, combining many source models and then looking at the total cosmic ray spectrum, all that is now being measured about isotropy, composition, and spectrum, is the way forward. And you'll be able to rule out a lot of models, I think, that way, including possibly the one I've just sort of outlined.
Okay, thank you.
Okay, now we have a question from Christoph Meissner.
Yes, that was a very nice talk. And it's exactly the problem that the content of these highest energy cosmic rays is mostly, we guess, iron nuclei, that we proposed with Hermann Nicolai that they come from the skins of neutron stars, which are naturally made of the iron nuclei and accelerated by whatever, Planck mass energy. So don't you think that the multiple going through the shock wave would disintegrate the iron nuclei, that they should come from somewhere else in a sense?
Well, not in the, there is spallation of iron, especially. There's a so-called giant dipole resonance, and photons can destroy iron as well as in fact that got the cross section for that got changed recently, so you have to be careful about that. So iron itself is a little fragile, but if you look at this decomposition from Aubert et al. 2020, you'll see that around this part here where the statistics are best, it's A's between 5 and 22 they're claiming. So it isn't necessarily iron, but I agree with you. I would put what you said the other way around is the difference. I would, I try to emphasize this, that it remains in my book at any rate a credible possibility that neutron stars do, particularly millisecond magnetars or something like that, you go to very high energies, are the source of a significant number of cosmic rays. Then you are looking at what you expect the surface composition to be, which is something like iron. I completely agree with that.
And they would not produce prediction. Yeah. They would not produce the gamma background that strong. So yes, that evades this problem with the gamma background. So
but I think for the gamma ray background, I think the old ideas to David Schramm and others, where they had quark nuggets and various other sort of exotic structures, which would be very exciting if there was some evidence for them, but it really that was a sort of what they called a top-down model, which was making things, you know, close to the Planck energy or whatever, and then having them create showers of particles cascading down to lower and lower energies. And we were seeing way down the food chain, as it were, at zeta electron volts. That was the original idea. And I think the problem with that is it vastly overproduces the gamma ray background that we have no problem explaining using more prosaic sources.
But not necessarily in this case, but okay, that's the way for debate. Okay, thank you very much.
Okay, any other question? I don't see any hand being raised. So let's thank Roger again.
Thank you very much indeed.
And so tomorrow we have the last lecture, where we will also hear about cosmic rays, but also about biological homochirality. So tomorrow, same time, and a link will be sent by Isabel before the meeting. So thank you very much again, Roger, for this very beautiful talk. And